Good afternoon, everyone. The first thing I want from you today is ask me any questions you have about the exam, anything you want, anything you don't understand, and then we'll do a few problems and then you guys will be on your own. Okay, so I definitely want to start with your questions. You guys have any questions about anything? Because I write comments on your homework and I have the solution. So anything you did not understand. Okay. There is one part, I will just talk about it briefly, and then I will go back to proof. So if you guys don't have any questions, okay, let's get that clear. Sorry. All right. There is one questions in your homework number 4, where I ask you to find, I gave you a sentence, and the question is find the domain and find, introduce predicate, write the sentence using predicate and domain. And it was not very good. Okay, the negation was good, but writing predicate and domain was not actually particularly good. All right. So I take a simple one, this one, for example. For every 2 integers, n and m, if n and m is even, then n is even or m is even. Okay, which we're going to prove today. But for now, I want to introduce predicate and domain. So first, what do we mean by the domain? What are we talking about here? We're talking about integers. So the domain are the integers. Okay? Part 2. Second, I want you to introduce predicate. So before I do that, I'm going to write something that I had issue with. So a student wrote something like that. P of x sorry, my apology. That's not what they wrote. I wish they did that. They wrote something like this. And even. What's wrong with this way of writing? So they're introducing a predicate and they wrote P of x and even. What is wrong with this, with what the student wrote? Remember, a predicate is a sentence that involves a variable, so that when the variable is replaced by a number, your sentence becomes a proposition. It means a true or false statement. What's wrong with this? What's wrong?
Applying one argument that n is even and it ignores the m.
So is this what, I mean, if a student to write this one for me, what does P of 1 mean according to the student? Right, according to the student, this would read an even, which as far as I'm concerned, that's not a statement. This doesn't make any sense to me. So what the student did is that when one of your classmates pointed out, if x is your variable, x should be your variable. So this should read P of x is x even. Okay, so the variable here has to be x, otherwise this is nonsense. Because in this sentence, if you keep it the way you had it, P of 1 will read an even. This is not a statement, this is nothing. It's not true or false. When I put P of x, x even, that makes sense. And then P of 1 will read 1 even, which is a true state. Okay, so when you're writing your predicate, you have to be very precise. Things should make sense, absolutely. So if I go back to this, exactly this problem, for every 2 integers, if n m even, then n is even or m is even. So the domain is integers for both variables in this problem. The predicate, you have a lot of choices in this case. So let us say I'm going to introduce 2. I don't really have to. Suppose I want to introduce a predicate for n m is even. Okay, so I have 2 variables n m. So that's one possibility here. So this should read that Q of an M to be N times M even. This predicate now makes sense, because if I tell you, okay, what's Q of 2, 3? Q of 2, 3 will read 2 times 3, 6 even, which is a true statement. So the predicate should make sense, should absolutely make sense. And I can introduce another predicate. Let us say P of X, X even. Now I'm going to write this using the predicate. So for every two integers, for every n in z, for every m in z, if Q of an m, then n even or m even. Now I only introduce P of X because it's actually the same attribute, but now here I have to write then P of n or P of n. Okay, so in other words, for all n in z, m in z, if Q of an m, then P of n or P of m. Okay, so when you write, it should make sense. You have to write it correctly. Now the negation would become there exists in n, there exists in m, such that Q and m, and non-P and non-P of n and non-P of m, which are two different variables. Means I can find an integer n and I can find an integer m such that nm is even and n is not even and m is not even. Okay. Right, problem number 2. Every student have seen every Star Wars movie. So I already have 2 quantifiers. Okay. Domain. How many domain we're going to have for this problem? How many domain? So what's varying here? Student and Star Wars movie. So in this problem, I need to have 2 domain. X, all the student at P and W. So the domain is a set. This is a set, not a number. That's a set. That's the set of all student at P and W. That's a set. The domain is a set. So student tells me X is the domain. This is not, that doesn't make any sense. The domain is a set, is collection of object, which is all the student. M is a set, which is the collection of all Star Wars movies, all whatever, 15 of them, whatever you want to call a Star Wars movie. Okay, so these are my domain. And then my predicate. Every student have seen a Star Wars movie. So my predicate is going to be, you can call it S, X, M. For example, mean. You have to be very clear. Student X has seen movie M. Now this will make sense because let us say, so if I write S of Rachel, comma, I don't know which one you want. Phantom Menace, one of them. Okay, Rachel, is this true or false? Rachel, is this true or false? What? It's true? Okay, and it's very precise. It means I'm saying Rachel has seen the Phantom Menace. That's a true statement. So my predicate has to make sense. Absolutely makes sense. So when I substitute something for X, something for M, I need to have a very clear statement. Okay, so that's how we really work with those. And now my statement will become every student means given any X in big X, every student have seen every Star Wars movie, given any M in big M, S of XM. That's how we write this using predicate and domain. That's how you introduce domain very clearly And that's how you introduce your predicate. That was a lot of jumble mumble in those ideas. And then the negation, that exists a student and there exists a movie such that the student haven't seen the movie. I mean, there exists a specific student and there exists a specific movie that this student haven't seen that specific movie. You have seen other movies, but not this very specific one. Okay, questions about that before we proceed? It's your last chance. Good. So now we're gonna go back to our ideas of a proof. I said I will do like 3 proofs today, and then you guys can go. So we can finish contraposition today. So let's see what our issue was. First, let's see what a proof by contraposition or contrapositive. Okay. So let's see what the idea is. It says me the following. Suppose we want to prove the following statement. Okay, suppose we want to prove the following statement. Suppose we have to show that for all x in D, if P then Q. Is true. Okay, and we try directly. It means we pick an x in the domain for which the hypothesis hold, and you want to try to show that the conclusion hold, and we couldn't move. Okay, then we can show the following. We can show the following is true, the contrapositive issue. Show that for all x in D, if non-Q, it means if the hypothesis is false, then, sorry, if the conclusion is false, then the hypothesis will have to be false. Okay, so that's what the idea of a proof by contrapositive. Okay, and sometimes it's more manageable than the direct proof. It really depends on the problem at hand. Okay, so we're gonna do the last one. Let's say 3 problems for that. So prove the following. And every time we try a proof, we usually start direct and we really stumble, and then we try contrapositive for today. So prove that for all nm in Z, if nm is even, if the product of 2 numbers is even, then one of them has to be even. That's the only way it could happen. So you take 2 integers, you multiply them by each other. You got an even number. So this is my hypothesis, and this is my conclusion. Okay. So as I said, there are 2 issues in this problem. First, if we try direct. So we're gonna try direct. Okay, there are 2 reasons that force me to change strategy. Okay, I say an m is even, it means an m is 2 times k. And then I have to show n or m even. That's really what I am kind of stuck. If I solve for n, I get 2 times k over m. But there is no reason for this is an integer. Is this in Z? I don't know. So that's really one difficulty in the problem. The other difficulty is, one of your classmates also mentioned it last time, the conclusion is this or that. This is actually usually not very easy to prove this or that. Okay, so if I have 2 issues that tells me, flip them, you may have better control. So, but at least direct is clearly, I can't go anywhere with it. So we're gonna do proof by contrapositive. Proposition. Means we have to prove. This is the domain. We never touch the domain. The domain has nothing to do with the contrapositive. The contrapositive, so that's the domain. We don't touch the domain. We want to show that. If non-Q, so that's my P and that's my Q. So my P depend on 2 variables and this one depend on 2 variables. If this is not the case, then this is not the case. What is non-Q? It means if n is odd, not even. M odd, that's the negation, then NM is odd. See how much easier this, going this way. What's helping me here is that I had an OR, it became an N. It's easier to work with an N because I have really two things to work with. I know something about that, and I know something about that. So already the proof is easier. And I need to conclude one thing, and M is odd. So this is absolutely much easier to work with than the previous one. Okay, so now let's see the proof. The proof is very easy. So let's prove now. Now it's a direct proof. Means we prove the proof by contraposition in a direct way. So we pick two elements in the domain, but not any two elements, such that they satisfy my new hypothesis. They satisfy my new hypothesis, such that N odd and M odd. Okay, and somehow I have to convince you that NM is odd. Okay, so that's what I know about N and M. That's really my goal. That's really my ultimate goal right there, that the product is odd. So we start working with them slowly. So what does it mean, N odd? N odd, hence, I can find K in Z such that N equal to K plus 1. M odd. M is odd. Again, I can find another integer. I call it K prime in Z. We have to make sure that my K and K prime are not the same. Okay, that's what I want. I know where I am. I know where I'm heading. So now I just take the simple product. I multiply them. So that's what I want at the end. And then I will get 2K plus 1 times 2K prime plus 1. So basically I'm showing the product of two odd numbers is odd. And I think I've done this before, but it doesn't matter. Now I just multiply. Because what is an odd? It's 2 times an integer plus 1. You want to show me something odd? You show me it's 2 times an integer plus 1. So it's going to give me 4K prime plus 2K plus 2K prime plus 1. Okay, so now we're going to write it as 2 times an integer plus 1. But my integer now is very clear. It's 2K prime plus K plus K prime. Now, this is an integer. We have no second thought about it because its product of integer is an integer and the sum of integers is an integer. So now we're going to write J to be what we think it has to be. This is absolutely an element of Z. So this is going to be equal to 2J plus 1J in Z. So hence, NM is odd, basically by definition of odd. That's really what odd is for me, by definition of odd, okay? So that's a very good scenario, very simple, but scenario where contrapositive is actually, much easier than going direct, much easier than going direct. Okay, I'm going to do 2 more problems along the line, as I said. Okay. If you're not done, let me know. I try to keep it a little bit longer. All right, now I'm going to give you the following problem. Okay. Let xy be 2 positive number. So example. Let xy be positive number. So positive. Okay, that's my domain. Show that if the product is less than 2, so multiply them, you get a number less than 2, then one of them has to be less than the square root of 2. Okay, so multiply 2 numbers, you get something less than 2. then I want you to convince me that the product, one of them, you multiply them, you get less than 2. You have to convince me that one of them should be less than the square root of 2. Okay. Is direct a good way to do the problem? Okay, I'll give you 2 minutes to think through that, and then you guys guide me through what you did. Okay, you have 2 minutes. Do whatever you do on a scratch piece of paper, and then you will share with me what you did. Okay, who's ready? Anybody ready to guide us through that? Don't make me pick, just volunteer. Okay, if you don't volunteer, I'll pick one of you. Okay, Tim, would you like to tell us? What are you thinking about?
So I decided that probably contrapositive would be easier because the conclusion, the then x is less than the square root of 2 or y is less than the square root of 2 is hard to prove versus the contrapositive.
Okay, so contrapositive, prove by contrapositive. Even if you go direct, it's a bit problematic how to get from here to here. So prove by contrapositive. So always the first line should be what you have to prove. Okay, so once, because you're doing proof by contrapositive, now what's going to become my statement? And then, so what's going to become this piece? Now on that, go ahead.
If x is greater than or equal to the square root of 2 and y is greater than or equal to the square root of 2, then x times y will be greater than or equal to 2.
Very good. So now that's what we have to prove, and we have to do direct proof for this new statement. So we're going to start with 2 positive number, but not any one. The 2 positives that satisfy the hypothesis. So let xy be positive such that x and y greater or equal to square root of 2. So that's what we have to start with. But my actual goal, my really where I want to get to is that you have that if x and y satisfy this condition, then this is the case. All right, so who want to guide me from here all the way here, every step justified? It's actually it's fairly simple, but let's do that. Again, as usual, if somebody is ready, share it with me, or I will start choosing as usual. How can we go from here to here? We can multiply both x and y. We have to need a justification for that. Why we can do that? Can we always do that? Can we always do that?
X and Y are in the real numbers, right? We can always
Yeah.
multiply real numbers.
No, what really will allow me to do that? Not because there's something very specific that will allow me to do that.
Is it because they're both the same? They have the same inequality?
No.
Okay, so I don't know if this is the right train of thought, but the condition for choosing x and y can be √2 or greater, right? For both.
Yeah.
So
yeah, we have to, because I have
Right.
to pick them that satisfy the hypothesis.
so
Right.
if that's our starting point and we can choose that and we know they're positive,
That's
if
crucial.
you start with √2 times √2, you're going to get 2, which means anything greater is always going to be greater than 2.
Yeah. But what's crucial was the fact that
We're always positive.
it's always positive. Without positive, I cannot say, okay, this so because fairly simple, you can say x bigger than something like that. If you take two negative numbers, then the inequality does not have to hold at all. So being positive is crucial in this scenario. Okay, so let x was as at x. So x bigger than square root of 2. Okay, so one way, I'm basically rephrasing it, so I can, since y is positive, then x times y is larger than y times square root of 2. Is this statement correct? Every statement we write has to be correct. Okay, is this correct?
Yes.
Because y is positive. Without y positive, this is absolutely nonsense. No, but y itself is larger than the square root of 2. So we have the following. xy is larger than y times √2. Y is larger than √2, so it's going to be larger than square root of 2 times the square root of 2. Okay, it means xy is larger than 2. Okay, it becomes so simple to prove the statement if we proceed this way. But definitely the positivity of y is absolutely crucial in the statement. Without that, my statement actually is fairly simply wrong. All right.
You go back to that.
What?
You go back. Thank you.
Sure. All right. Can I move on? Yes
Yeah.
or no?
Yeah.
Yeah, thank you. Now we're going to define, or not, we defined already rational numbers. So let us remember what rational numbers are. So you guys, what's the rational number? You remember what they are? Rational number are all numbers of the form
P over Q, where P and Q are integers and Q is not 0.
Yeah, crucial. Q non-zero. And we actually gave them a letter. We call it Q. Q is the set. So basically, Q is all the P over Q, where P in Z, Q in Z, Q non-zero. Or all the rational number, which is basically rewriting the set of all rational numbers. Now, irrational number irrational number. Okay, so irrational number, it's a number which is not irrational. So irrational number is a number that's not rational. Not rational means a number that I cannot write in the form P over Q. Means a number that there is no way I can write it in the form P over Q, where P and Q are integers and Q different from 0. And so irrational is nothing more. Sometimes we can write them at R minus Q, everything, every real number which is not irrational. This is the set of all irrational. Okay. Now, very soon, or probably I'm sure a lot of you know that there are numbers who are not rational. There are irrational numbers. And one of the most famous one is the square root of 2 is irrational. And we're going to prove that, definitely. We're going to show, I have to convince you that the square root of 2 is irrational. So, but for the time being, let us accept that. And next hour, probably, we will prove that. Okay, it means there is no way. What does it mean? There is no way you can take the square root of 2 and write it as the ratio of 2 integers. There is no way you can write it as the ratio of 2 integers. Okay, that's what irrational means. Okay, so now I want you to show me the following statement. Prove the following. Okay, let A be a real number. No, let A be in Q. So now I'm very precise about A, and B, a real number. So A, that's the domain of A, and B is a real number. Show that. If A plus B is irrational, means not rational, then B is irrational. Okay, so it means we take the sum of two numbers, A and B. If A plus B is irrational, it means I cannot write A plus B as P over Q, then I cannot write B as P over Q. Okay, again, as usual, I want you to think about it a little bit, and then we discuss it together. All right, anybody ready? And whatever proof you picked, because the only thing we know now is direct and by contrapositive, you have to tell me why you choose what you choose. Who's ready? Patrick?
Yeah, I'm here. I'm just kind of struggling with this.
Okay. I mean, I should memorize your voices. I usually memorize your name and your faces, but now it's the voices I have to deal with. So,
Sorry.
okay. Anybody else? Did you try direct?
I tried contrapositive because I think it's simpler to use rational numbers to prove than irrational because we have a better understanding of the form of a rational
That's a
number.
good point. Irrational, it means it's not rational, which is already a difficult issue.
Right.
Right? So I want to show if something is not this, then the something is not that. That we barely understand, actually. So it will be easier if I do the contrapositive that if this is rational, then this is rational, and there is more hope in the proof. So every statement that tells me what really to do. So there is.
Sorry, can I ask a question?
Of course.
This is the part that confused me. Is a number that is not irrational necessarily rational?
Absolutely.
So
because
like
what's the
what?
definition? Yes, because what's the definition of irrational?
That is not rational, sure. But
Right.
I guess I'm confused by like how complex numbers fit into that.
You're absolutely correct. I'm working with the real numbers.
Okay.
So you're right, because I'm not so a real number is called irrational. So I will add that. Does this make more sense now?
Yes.
Yes. And actually, when I put it here, I put R minus Q. Is this?
Yeah, I got, I don't know, whatever.
No problem. Confusion is good for us. Very good. So now we're going to do by contrapositive. So we put it and then we prove it. So prove by contrapositive. So again, we rewrite because we prove by contrapositive, we have to rewrite the statement that we have to prove. So we're going to rewrite it. So let A be. A is in Q. So as I change my domain, we don't touch the domain. This is the domain of my variable. That's not the part we touch. It's the statement itself. Let A be, we're going to prove that. If B is rational, then A plus B is rational. Okay, so if B is rational, then A plus B is rational. And we have to be very careful with the domain. I mean, my domain is very clear. All right, so now the proof. How can we prove that?
So once we write, when we do a proof by contraposition, once we rewrite it, we're still, now we let the negation of Q be true, and we assume that's
Exactly.
true. So
Right.
so in that case, it actually works for the domain, because if we let B be rational and just accept that's true, it kind of takes the difficulty with using any real number out, right? Does that
I
make,
followed you till you tell me if
Okay.
it B is rational, then this will remove which difficulty?
so if you let B be rational, you've isolated it, you've taken out the rationals from the real numbers for B.
Right, absolutely.
So now if you let B, so that means you can say B is equal to the form P over Q where Q isn't 0.
Correct.
And then we know A is part of the rational number, so it also assumes that form. So we could say R over S, which is equal to those being both integers and S isn't 0. And then I think we've proved before where if we have a rational number plus a rational number, we do where we get common denominators, add them,
Exactly.
and we prove
You
the
can use-
bottom isn't equal to the 0.
Yes. And you can use something we proved already if you want.
Yeah,
Okay,
I
so
wrote it all out, but I'm pretty sure we've done that before.
Yeah. I'm sure I did because, when our attempt to understand how to work with those, I usually make sure I do those problems. And you have the freedom to use something we did if you know how to do, if you use correctly. Okay, so, but I will redo that just because it's simple. Okay, so, but what you said is correct. We did prove that the sum of two rational is a rational number. And now I am actually dealing with two rational numbers because, I'm not dealing with irrational, which is make it hard for us to work with. So let us prove. So we're going to say let A in Q, so A is rational, and B in R, such that B is also rational. So now, as your classmate is trying to tell us, I removed the condition that B is irrational. So my B now is rational and my A is rational. And my goal is the sum. I never lose track of where I'm heading. Okay, now I say, okay, A is rational. A in Q, A is rational. It means A is whatever, R over S, R S integers, S non-zero. B also is rational. So writing B rational or writing B belong to Q is exactly the same thing because that's really what Q is. It means again, B is P over Q, PQ in Z, Q non-zero. And now I'm looking at the sum. And as we did last time, finding common denominator and proceed. My common denominator is SQ, and this is RQ plus PS. Okay? Or if you want, you have the right to say the sum of two rational is rational. So A plus B will be rational. I'll give you the permission to do that. And now this is my numerator, my denominator. I can call this, let us say I, whatever, and it's going to call this J. So I is in Z, J is in Z, and J is definitely different from 0 because Q is not 0, S is not 0. So when you multiply them, you get non-zero number. And I have A plus B is I over J, I, J in Z, J different from 0. So hence A plus B is rational by definition of rational number. Okay. So definitely what really made me use proof by contrapositive is that I need to prove that something is not rational, which is not easy, not easy. So I would rather work with rational than that. Okay. All right, I finished with putting one more problem in front of you. And we talk a little bit about it and then we stop. So my last problem is the following. Okay, so we studied two approaches to proof. I usually start with direct, and then if really I don't know what to do, I move to contrapositive for the time being. Now, let us say I'd ask you to do the following problem. So we accepted the following fact. We accepted, as I said, next time we prove it, that this number, there is no way we can write it as the ratio of two integers. So we accept this fact for the time being. And now I wanted to prove the following. Let A be a real number. Show that if A is rational, then it's irrational. So I'm going to give you again 2 minutes to interact with this problem. Any input? Anybody has any idea how they are approaching this problem?
Can we prove it directly?
Directly. I follow anything you want. I write them down, so you guys don't have to write, but I write what you said directly. How would we gonna do that? So direct. Okay, let A be in R, such that for this A, the hypothesis is satisfied.
Okay, so assuming A is any rational number, so it doesn't really matter what number A is. A is any rational number. The kind of the phrase in the bottom part is going to be A squared plus 2 under the radical, right?
I'm lost. Where is the A square coming from?
Well, am I doing this right? Can you add, if I could take the square root of A squared and then I could add numbers that are both in the square root.
No.
No?
If I understand well, correct me if I'm not understanding well. What I'm understanding is the following.
Yeah.
right?
Yeah.
This is what I'm understanding.
Yeah, I think.
This correct?
Is that correct?
Yeah.
Okay.
I'm asking, is this correct?
I'm not 100% sure. I thought it was, but I'm no.
No.
Damn.
No, you cannot. Remember, let me give you two simple numbers. If I take square root of 9 plus 16, okay?
It's 25, yeah.
Right. Can you break the square root?
No, you can't. Yeah, that's right.
Absolutely not. Absolutely not. Okay? We cannot break the square root. If you have a addition, we can break it if you have a product, but not if you have an addition.
That's right. My brain's just broken right now.
That's okay, that's okay. I don't care about that. Yeah, keep going. Can we go from there? Anybody? So if I start and I go to a plus square root of 2, what will I get? P over Q plus square root of 2.
Oh, like because you'll never be able to express square root of 2 as a rational number, you're never going to get it to be a rational number. And since it's not, it's going to be irrational. It's basically the answer, but I don't know.
So, I mean, okay, this is irrational because I cannot express this as irrational.
As a rational number.
Yeah, I will not accept this. So what's the role of a rational is? So what the role this is playing?
Would you get similar bases or whatever?
Repeat.
Would you multiply square root of 2 over q by over q?
Common denominator.
Yeah, it's common denominator.
Okay.
And then from there, you can say that the numerator, I'm not sure where to go from there.
Mm-hmm. So we're having trouble, aren't we?
Yeah.
So
Direct is the wrong approach.
it's not the right approach.
So just I don't think this falls into direct or contrapositive, but if we had a plus root 2
Mhm.
and so if it where do I want to, I'm trying to figure out how to word this, but if root 2 was rational, like let's just say it was, that would mean
Yeah.
the sum of a and root 2 would also be rational. So is there any way we can set a plus root 2 to equal the sum, which would just be like m over n or x a over, or not a, but like r over s, like in the last problem, and then we
Okay,
can
so-
say,
Uh-huh.
and then we can say like root 2 is equal to p over q minus r over s, and we know that's always rational. So
Right, but that's
like,
not
and we
contrapositive.
no,
Yes.
that's why I said it's not either of those. But then if we accept the fact that it's always irrational, we have an
Right.
irrational equaling
Right,
irrational.
right. So we need another way of proving things.
Yeah, that's where I'm trying to go with this.
Right. So we need another way of proving things. So let us totally discuss this problem. And I'm going to stop there because that's what's going to be the heart of what we're going to do next time. I want direct. Direct show me that if A is rational, this one is not rational, which was, as we realized, was hard. What will be the contrapositive? The contrapositive would be, we assume this is rational, correct? If you don't
Yes.
tell me yes, I will stop.
Yes.
In the contrapositive, we assume this is rational, and what we prove? A what?
Is irrational.
Is what?
Irrational.
Irrational. Am I looping? Do I still have a problem?
Yes.
I want to start that something is irrational, which is actually hard because not rational. So this is a situation whether I move direct, I have trouble. And I use the contrapositive, I have trouble. So the question is how to handle those type of problems. Okay, so neither one approach work perfectly the way we want it. So the question is there another approach to prove that help me to get out of this loop I am working with? Whether I go direct or contrapositive, I have really an issue. And that's what your classmate is actually trying to hint to, but we have to make it into a correct mathematical idea. How else can we prove it? And the idea will be, what we're going to work with it next time, is the notion of a proof by contradiction. And that's going to be our third attempt of trying to prove a statement. So sometimes direct, sometimes contrapositive, and sometimes none of them would work. So we need a third approach to prove, and that will be what we will be calling a proof by contradiction. And that's what will be the content of what we will be doing next time. And the idea is that, we have a situation that nothing works. So what can we do? We still have to learn how to prove. All right, so I'm going to stop right now the course for today, the lecture for today. Next time we go from there. And I think I opened the exam, I think like either 2 or 150. So you guys can go take a break, and the best of luck. Do you have any questions for me before I let you go? Any questions?
You say the test is to 1:30, right? The 1:59.
I think it's 2 o'clock until 11:59 tonight. The test does not require all that time. The test will require at most an hour and a half. It doesn't mean all this, but I'm giving you a lot of time.
Okay.
Okay, so it opens at 2. It closes 11:59, and this is Hammond time. So don't confuse the time for those who live in Illinois or I don't know. So it's always Central time, not Eastern time.
Okay.
Okay, good luck, guys. Bye-bye.
Okay,
Wait,
thank you.
wait,
If you have
so
questions, ask.
the
Yes.
test is going to open and we have till midnight to finish it. There's no time limit on it.
Exactly.
Okay, good.
Anything else? You better all get 100% on it.
I'm going to try. Thanks. Bye.
Okay, bye-bye, guys.